Hello.
Hi. Mr. Rosenthal.
Hi. Volume of prisms. Great.
Good morning, Mr. Rosenthal.
Morning.
What's the Snapple fact?
There isn't one. I only have plastic bottles now.
Oh.
You guys want to see the board? There's a bunch of calculus on there. That's a proof of the derivative or the power rule.
It's sort of confusing.
Sort of. You don't have the prerequisites to understand what you're seeing up there. But you will soon.
Tomorrow?
This is slope. D is for delta. This would be delta y over delta x. You will use limits when you cannot land right on something, but you can see that the behavior is approaching something, kind of like infinite sides of a polygon. We can't get to the infinite, but we know what's going to happen when you get there. So that's what we do. And here you'll see h as a denominator. What this means is that h can't go all the way to 0, but the value of this is going to start looking a certain way as you get closer and closer, so that you can know what the value would be if you were able to make h 0. We manipulated the top using. I'm getting an echo effect with somebody here. We manipulated the top so that we could get an h using the distributive property factored out. So h over h canceled out of the problem. So we didn't have to worry about making h 0 anymore. And then on the top, we can make h 0 and then cancel things out until we got what we wanted to show. Is that if you start with an exponent of some exponent, the derivative of it will be taking that exponent down as a coefficient and then taking one away from the exponent. And that's how you do a derivative. And this is how we proved it. Anyway, let's start. Let's go back to geometry. At some point, you should be able to move freely between all the maths. It's all connected. It's all one thing. Okie dokie. So we're going to talk about volume. We already mentioned it. So
Hi, Mr. Rosenthal.
hello. So you already have the prerequisite, but I like the Post-it note idea. Or start with dimensionality. A point has no dimensions. We stretch it at a right angle to itself, which could be any direction. And now you have a segment, which is one dimension. Stretch that segment out at right angles to each vertex. So right angles. And now you have a 2D object, a rectangle. Okay. And then, so that rectangle we learn has a base and a height that you can get the area of. That's how many little squares fit in here. But each of those squares are flat. Okay. All right. So if we want volume, we need another dimension. So we
stretch it again at a right angle.
Right, towards you or into the board. And we have to somehow represent this on a flat plane. So the way we represent it on a flat plane is like, kind of like creating a shadow of what it would be. If you shined a light through the three-dimensional object and it was transparent, you might get a shadow of it.
Translucent.
Yeah, it would look like this. Okay, and so the shadow of it on the board would look like that, but it would actually, everything would be at right angles to each other. So you would have a length, you would have a width, and you would now have a height. And you could think of it as a stack of Post-it notes, where you started with one that it did have some height to it, actually. But if you imagine that each Post-it note imagined that it had no height, and then you just stretched it up. Now you have the stack, and what you've done is you've created another location where the top of the pad is versus a location straight below it. And we can measure how far apart they are, which would give us a height dimension. Okay, so a change in position gives you a displacement, all right, in physics, all right? So what we can do is we could think of it as, well, we had a square area down here on the base, right? And then we made H amount of those squares all the way up to the top, okay? So now you had a square, you were counting those squares, but now each square lifted up, and we want to count in units. So we'll count them one at a time, okay?
Mr. Rosenthal?
Yeah. So we lift that one square up, and now that square gets lifted up, and now you have all these cubes that fit inside there. And each cube is 1 by 1 by 1. Just like every square on the flat bottom was 1 by 1, every cube is 1 by 1 by 1, and you can now count how many cubes are fitting inside that rectangular prism. And that is what we're doing when we find the volume. Now, if you noticed how I did it, I took one area. This length times width gave me the area. And I multiplied by how many of those I had. Okay, so the way I'm going to say is, I'm going to call this area down here the base area. Capital B means base area. And I'm going to multiply that times that one-dimensional height. The base area is 2 dimensions. The height is 1 dimension. What happens when you multiply 2 dimensions times 1 dimension? If you add them, you don't get anything. But when you multiply them, and they're at right angles to each other, you go into the 3rd dimension. So 2D, which is the area of the base, times 1 extra dimension of height being multiplied to it, not added, multiplied to it, creates a 3D volume. Okay?
Sure.
Yes.
A few questions. First of all, isn't the base 1D and the height is 2D?
The base is 2-dimensional.
How?
It's a square area on the bottom that I shaded.
Oh.
You could count how many little squares fit in here.
Also, can't you calculate the height with length times width?
You don't calculate the height with length times width.
Yeah, because isn't the length times width equals the base?
Right, that's the base area. And so now you have the area that one Post-it note takes up. Now what you're going to do is you're going to stack all your Post-it notes up.
Well,
right?
can't you like divide it into like lines and then just flip? Then one of
You don't want to do it that way. Then you will not understand volume going into the future. The way you want to understand volume is by stretching dimensions into more dimensions. And then in this last phase of it, these squares would all stretch upward and they would become cubes instead of squares. All one by one by one. And what we're going to want to do is count them without having to count them, right? Just like in area, instead of counting all of these, you could say, oh, it's 3 by 4. Instead of counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, you know that you can do 3 times 4 is 12. 3 rows and 4 columns is 12 squares. Okay? So we can count how many cubes there are the same way, right? It will be the base area times the height, right? If the height is 2, then you would have 2 of these cubes stacked upon each other, right? One cube on top of the other cube. All right, so it would be 1 by 1, and then this distance would be 2, right? So you have a base area of 1 here, right? And then times 2 units of height to that, right? So you would do a base area of 1 times a height of 2 gives you a volume of 2. And look at how many cubes there are there. There's 2 cubes. So now we're counting cubes. By taking the base area and multiplying times the height, you are counting how many cubes are inside the object. Just like in area, when you did length times width, 1 dimension times 1 dimension, you're counting 2-dimensional squares that are inside by doing that. Okay? And that's basically what you're going to do. And because of our training yesterday, I don't have to do this with a rectangular prism. I can do it with a triangular prism. I can do it with a circular prism, also known as a cylinder. Okay, and then later on we can do it with pyramids. You're going to lose something, just like you lost when you lose a base and it converges into a point, you're going to lose some of your volume. Okay, and it's actually a cool amount of volume. It's going to be a specific amount of volume you lose every time by doing that. But we're not there yet. Right now, let's not lose any volume. Let's keep all of our volume and measure how many cubes, and it's simply take the dimension we were working on, area of the base, and just multiply it times that extra height you're going to give to it. Okay? And that's it. And that's going to give you volume of any prism, even cylinders. So that all you have to do for a formula is just this one formula. Area of base times height is all you need to know. And then that you can do it for any 2 base polyhedron. Okay? And let's share screen and move on. Okay, so the volume is the measure of space occupied by a 3-dimensional region. It is measured in cubic units, feet cubed. Okay, so this one, go ahead and calculate the volume of that one, please. Go. 630. I didn't get 630. I didn't get that 0 there.
They might have like not the decimal point.
Yeah, you lost your decimal. I'm looking at that chat, looking good so far. Make sure you don't put the cubed over the 63. That would be wrong. That's a giant number, by the way. 63 times 63 times 63 is not correct. It's what you're counting. You're counting 63 cubes fit inside of there. So let me unshare the screen so you can see what I did.
Well,
Okay. So what I had here is I wanted the area of the base. Well, the dimensions that made up the base were the 3 and the 4.2. So I multiplied those to get the area of the base. Then I took the area of the base and I multiplied it times the height of the prism, which gave me 63. All right. Some people will just memorize it as length times width times height. Just multiply the 3 in any order. That would be fine. The reason I don't do that is because I want you to use the same formula for all of them. There's better connectivity in your conceptual understanding of it. It's more connections made when you can just use one formula and understand that they're all the same thing. All right. When you do, okay, this one is length times width times height. The next one is length times width times height divided by 2. This one is 2 pi r squared plus 2 pi rh, you know? And every single object, you have to memorize a different formula. Then they just look like different problems that are disconnected from one another. If you understand all of the two base objects are the area of the base times the height, you have a better understanding of volume, and you're going to have a better understanding of surface area. Questions about this? Okay. Okay, let's move on. Go ahead and do this one. Example 2. While you're doing example 2, I'm going to clean my eraser.
Mr. Rosenthal, do you know how to do superscript in
Shift 6?
Shift 6?
I think so.
Okay. I got this like arrow pointing.
Look at your keyboard. It should be, yeah, it should be an arrow pointing up. That is an exponent.
Oh, so then you just put the number right after it?
Correct.
Okay. Thank you.
Mm-hmm. All right. So in this, what is this object? Is it a pyramid? Is it a prism? What is this thing?
It's a prism.
What kind of prism?
Triangular prism.
Yeah, it's a triangular prism. So what is the base made out of?
2 triangles.
It's 2 triangles. So if I need the volume, and the volume is the area of that base times the height, this right here is the height, the 7 centimeters. How do I know that's the height? I know that's the height because the height is always that distance that connects the 2 bases. So the 2 triangles are the bases. Where are the connecting pieces between the bases? That is the height of your prism. So even if I turn this on its side, the height has to be the connecting piece. It doesn't have to be, base does not have to be the bottom. I could rotate this so that the rectangle in the back there is actually sitting on the floor, on the bottom, okay? It doesn't change the fact that the triangles are the bases. Where I place it, so base, I want you to disconnect that or unlearn that from your mind, that base has to mean bottom. It does not, okay? So the two triangles are the bases no matter how I rotate it. That means the height doesn't always have to be going up and down. That's something you have to unlearn. Your instincts say, oh, the height is whichever one is going up and down. So if I turn this on its side so that I have the two going up and down, the two does not become the height. No matter how I rotate it, the height must be the connecting pieces between the bases. That has to be the 7. Well, then that means that if I know that this is 7, it's my job to find the area of the triangle, the base. Well, if this is 6 here, because that's 6, then I have the 2 dimensions that I need for the triangle. Okay, so the area of this triangle is half its base. I'll use little b so we don't get it confused with big B, and little h, which is, maybe I should have called this one big H, so we don't get them mixed up. So the height of the big prism is h. Little h is not just the height of that triangle. Okay, and we have those measurements, 6 and 2. So 1/2 6 times 2, okay, which is just 6. So the area of one of the triangles is 6. So then you multiply that times the height, right? And you get 42 centimeters cubed is the volume. And we're done.
Yippee.
Remember, I didn't use a separate formula. I didn't do length times width times height divided by 2. I could have. I could have told you that if you would have doubled the triangle out to there and doubled it down there, then you would have had a rectangular prism cut in half. So you could have just done base times height again and then just cut it in half. So that would have worked. Okay.
Base times height divided by 2.
Yeah, you could do that, but I'm using one formula so that I don't have to memorize separate formulas. I know it's the area of the base. It just so happens that the base is a triangle, and I cover that half by finding the area of the triangle. I have to take half, right?
Yeah.
Because I don't want to learn new formulas. I just want to use the ones I already know. I already know the triangle formula has half. I don't want to relearn that there's a new one called the triangular prism formula. I just want to fall back on the ones I already know. So I want the base area. It just so happens that it's a triangle. So that tells me I need to use this to find the area of it, times the height, which is 7. Okay. Try those, and it gives you the answers so you can check your answers with those. But I want to see if you can calculate it to get those answers. Go.
It already gave us the height, right?
What's given is what's not in pink. Pink is the answer. All the black writing is what you're given.
Oh.
Notice these problems have those perpendicular marks. They have to give you those so that you know what 2 dimensions are working together to give you the area. What I don't like is they should have tried to trick you here. They should have tried to give you the slanted length. Because then if I do that on a test, some of you are going to get fooled by that.
I got the second one.
What happened to the first one?
I'm gonna do it right now.
I got the area of the base is 52.
I got both of mine correct.
Don't you take half of 52?
520 plus 260 is 780.
Mr. Rosenthal?
1 second.
I got the other one too.
Cubic inches.
Don't you have to take half of 52?
No, because that's the base.
No, you're right. No.
Because it's a
You're right.
triangle. You have to
Right.
take half.
You're right.
Or you could just do the base times height and then divide that all by 2, and you would still get the same answer.
90. There we go. Oh, now it matches what it says.
Is it okay if I did the base? I figured out I did the base and then the height and did base times height and then divided that by 2, because I still got 390.
What base did you use? What do you mean by base? Base
Yeah.
area or base?
The area of the rectangle.
No,
On
that's not the base. Then you're failing to understand what we're trying to teach you. Is that is not the base. That's incorrect to think of it as the base. Now what you're doing is you're thinking of it as a rectangular prism and cutting it in half. I understand that you're doing that. That's fine. It's not that you're wrong, but you're not learning what I'm trying to show you. Is I want you to learn that the two triangles are the bases. Find the area of the
Okay.
triangle, and that is the area of the base.
Okay.
Yeah. So look at what I have. The area of the base is the area of the triangle. The height of the prism connects this triangle to the other triangle. Oh, it's the 15 does that. So the height of the prism is 15. The area of the triangle is 26. 26 times 15 gives you 390 cubic inches.
Mr. Rosenthal, that's why length times width times height is like sometimes not the most effective equation.
Not always. I mean, it's not that it's false though. It's not
For
false.
triangular prisms, because you can get confused by just multiplying the length and the width and not dividing by 2 because it's a triangle.
Mm-hmm. Okay, so this is 5.2, 6.5 millimeters, 7 millimeters. Okay. Don't take the area of the rectangle on the bottom. You could, you're doing length times width times height divided by 2, it would work. But I want you to try to do it in terms of the two bases and the height. I really need you to start thinking that way. So it's going to be 6.5 times 7 divided by 2. Okay? So 40, that's 45.5 divided by 2. 2275, 22.75. Okay, so I got the area of the base is 22.75, and the height that connects the two triangles is the 5.2. The 5.2 connects the front triangle to the back triangle. So then you do.
Oh, and the area of the front triangle is the area of the either triangle, because the areas are going to be the same, right? If it's a triangular, then the area of both of the triangles is going to be the same, right?
Exactly.
And so you just need to take the area of one and then divide it by 2.
Mm-hmm.
Okay. And that's the base, and then you multiply.
No, you don't take the area of 1 and divide it by 2. When you take the area of 1, because it's a triangle, you have to divide by 2.
Yeah, that's right.
You don't take the area and then divide by 2. Then you would have divided by 2 twice.
That's
I
what I
know
meant.
you knew what you meant. I want to make sure we're being very technically clear.
And then you'd multiply it times the, like if you were to flip the prism over so that the triangle is facing down, you multiply it times the height, which is
Yeah,
a
you don't have
5.2.
to. Yeah, you don't have to flip it around.
Okay.
You just know that the base does not have to be on the bottom.
It just helps me understand it that way.
But that's training wheels. You want to come away from that as soon as you can. Try to start letting your mind understand that base does not mean bottom. All it's going to do is actually confuse you, not help you. So what you want to do is, what are the bases? Not the bottom. They are the two congruent area figures or planar figures, the triangles, the rectangles, the trapezoids, the octagons. Whatever the two of them are, the rest of them are rectangles, if you notice. They go around them. We talked about that yesterday. Those are the two bases. You want the area of one of those bases times the connecting piece, however long that is, gives you that extra dimension.
Okay.
Good.
Mr. Rosenthal? Is that millimeters cubed?
Millimeters cubed.
Okay.
All right. Any other questions? All right, let's take a look at this one. A room air conditioner can cool a room with a volume of 1,600 cubic feet. If a room has a height of 8 feet and a length of 16 feet, what is the maximum width of the room? Try to do that problem. Assuming the room is a rectangular prism, right? Say that that's the room. And you can put your answers in the chat. Nobody yet. Oh, no, there's lots of people. Never mind. Haley, Ben, Tanya, Julia, Rachel, Madison, Nathan, Tanya, all of you got it right so far. Put your units too, if you did not already. Most of you put your units. It's not, your answer should not be in cubic, because you're finding what? You already know the volume is in cubic. You're finding the width, and the width is only one dimension. So your answer should not be in cubic measurements, and it shouldn't be in meters either. Look back at make sure you get your units right. Always look back at the problem so you remember what units we're using. We were talking about feet, not meters. Make sure your answer makes sense. And if you have an 800-foot room width, does that make sense? Think about a room 800 feet across.
Oh gosh.
Okay, so if a football field is 300 feet, you have 2 2/3 football fields across a room. Yeah.
Powerful air conditioner.
Yeah. So something went wrong if you got 800. Okay, great. All right. So now let's go ahead and look. Most of you are getting it. Okay, here we go. Take a look at what I have. Drawing diagrams is very helpful. If you get good at drawing rectangular prisms, I'm not great at it. I can get one up there to help me do the problem. They told me the volume, I put it inside. They told me the height, I labeled it. They told me the length, I labeled it. They didn't tell me the width. They want me to find that. Guess what I did? I put a variable. Great. The area of the base, the good thing about a rectangular prism is you actually do get to pick what the base is. All of the faces have an opposite congruent face to it, right? Front has a back. The right has a left, and the top has a bottom. So if you made the right side face the base, then the left would be the other base. So the cool thing about a rectangular prism is you get to pick which of the base is. So you could always make it the bottom if you do like to do the bottom, which is what I did. I said the base is this length times width. There's your base, area of base, times the height of 8, right? And then you can multiply 16 times 8 if you want, but I don't want to do that. I want to divide by 16 right now. Now I just have W times 8, or 8W, is equal to 100. Divide by 8 on both sides, and you get 12.5. And that's feet. The width is 12.5 feet at most. If you go over 12.5 feet, you will not, the air conditioner will not sufficiently cool the room.
Mr. Rosenthal,
Mm-hmm.
is it okay if we did the base as the length times the height, like that rectangle in the front?
Yeah, the rectangle in the front can be the base. Yes, because it's a rectangular prism, you have the freedom to make any face you want be the base.
Yeah, because I just did the base and it was like 128, and then divided 1,600 by that.
That's fine. But
Okay.
just remember, all the other polyhedrons, you cannot do that. You have to use the actual base wherever it might be. And it could be in the front, could be in the back, could be in the left, right, top, or bottom. All right, so, but with the rectangular prism, you actually get to pick which one you want to be the base.
Okay.
All right. Try that one, see if you can calculate what they said is the answer. Draw a diagram for practice. Just practice working that problem out and check your answer with the answer the book gives. Sometimes the book's wrong, so maybe we can hunt to see if we can expose any incorrect answers that the book might have. Okay, so we have a rectangular pool. Okay. 17 cubic feet of water, 17.5 cubic feet water. Is the width, oh, same thing. Length is 3.5. This doesn't really do anything new for us. Not a fan of the 1 foot. This is a wading pool. Oh, it's a, yeah, it is. It's a children's pool.
Oh. Wow.
Okay. There's my base area times my height is 1. I have that.
Children's pool.
And yeah, it's just going to be 5. So when you do this, you're going to get a width of 5 feet.
Are these one of like the inflatable pools? Or like kind of
Yeah, if you look, it's actually pretty small. And it's not drawn to scale because my length is less than my width.
you can just switch the two.
Mm-hmm. When your drawing doesn't match the numbers, you just say, here's how you explain it away. You have an excuse. You just say, not drawn to scale. And then you're free to go.
Yep.
You won't get in trouble.
Are we gonna have to like draw kind of like a scale on the test?
No.
Okay.
All right, volumes of composite figures. Okay, now we'll get a little bit more fun, but it's not really much more. You know what composite now means from finding the area of composite planar figures. What do I mean when I say planar figure? What's a
Plane.
2D? Yeah, it's flat. So we found the areas of composite planar figures. Now we're going to find the volume of composite spatial figures. Spatial is three-dimensional.
You have to add the volume of the different figures.
Yeah, exactly. Go ahead and do that problem right there.
It's basically the same thing with area, but it's three-dimensional now.
Yeah, there you go. So now you can start finding volumes of things in the real world because you can piece together the different areas. Or you can, if it's not an exact something, you can estimate something's volume. By the way, once you know what the volume is, you can start working with density, right? In your science class, in your physics class, because what is the formula for density? You guys remember without looking it up? Density is equal to what?
Mass divided by volume.
Yes. Mass divided by volume.
Yeah.
Okay.
So we can find the density of
Yeah.
composite.
I'm trying to show my son about that because he's really into building boats with his Legos right now and going to the sink and seeing if they float.
That's cool.
Right? And then he's watched this video called Science Max, and
A little project on YouTube.
they were talking about a tinfoil boat they were trying to make work in a pool. And, it's a matter of how dense the object is versus how dense the water is. Whichever one is denser is going to sink down below. Well, if you want to have less density, you can do two things. You can take away your mass. If you look at my screen right now, switch to my screen. You can take away your mass, or you can add volume, right? So if you make a ship that has a lot of volume, but you're keeping the mass the same, you're stretching it out, your density goes down and so your buoyancy goes up, right? Your ability to float goes up when your density goes down. They're inversely related. Okay, let's get to this problem.
Should we put our answers in the chat?
Yeah, put your answers in the chat. Let me take a look at what you guys are coming up with. See, now I haven't even started the problem. Just want to see if you guys are getting the same thing. Oh no, I'm getting almost all different answers. Okay, now I'm starting to get a repeat answer. I got a 96, a 360, a 66, a 66, a 66, a 46, a 66, a 66. So it looks like 66 if you're doing, like Who Wants to Be a Millionaire, and you go with ask the audience. Usually the audience has it right, but not always. I see 40, a 66 again. All right, I'm going to start working on the problem.
I think the triangle is throwing it off.
Could be.
The triangular prism. I think maybe people got confused with the 3 feet at the end, but the 3 feet is still the same for the ramp part. That could be the case.
I drew mine slightly different, from a different angle. So this here is 3 feet.
It's good putting it in your own perspective because sometimes the problem itself does not give you the best angle.
Oh, I did not draw to scale though, because my 10 feet is shorter than my 6 feet. No big deal though. And my 2 feet is longer than my 3 feet. Doesn't matter. Okay, so I want to find the volume of each one separately. So let me find the volume of the rectangular prism. The base area is 18. The height is 2.
Oh, I see how people got 96.
So I got 36 cubic feet for my rectangular prism. I'm going to stop sharing the screen now. So this was, my base area was 6 times 3 was 18, times 2 was 36. Now for this one, I'm not using the rectangular bottom here. I want the area of the triangle. So it's 10 times 2 is 20. divided by 2 is 10. So the base area here is 10. The height connects the two triangles. So that's this, which is 3. So the height here is 3. So then I get 30 is my volume, cubic feet.
Yeah.
Put them together and I get 66 cubic feet total volume. Done.
Yeah.
Questions about that?
I think like how people get confused when it comes to triangular prism because they don't add by 2 or like multiply by 1/2.
Mm-hmm.
That's why 96 was in the chat.
Mm-hmm. Yeah, 96. They forgot to divide by 2, exactly. So if you got 96, you didn't divide your triangle by 2. You did 10 times 2 is 20 times 3, 60. You got 60 for the volume of your triangular prism when it should have been 30. That's probably the most common error.
Yeah.
I got 40 as one of the answers. I'm wondering how that came about. By the way, if you know the area formula for a trapezoid, you could have done this. You have a trapezoid here is one base, and a trapezoid on the back is a base, right? So the bottom base is 10 plus 6 is 16. The top base is 6. What's the average of 6 and 16?
6 and 16.
It should be 11 times the height of 2 is 22. So 22
Times 3.
22 is the area of the trapezoid times the height that connects the two trapezoids, which is 3. So 22 times 3 is 66. So you could have done this as a trapezoidal prism. This whole thing together is a trapezoidal prism.
Trapezoidal.
It is. The base of it is a trapezoid.
Yeah.
And you have 2 of them that are identical and a connecting piece, which is the height of it. So you could think of it as a trapezoidal prism and just do one calculation.
That might be easier.
Yeah, because trapezoid is average base times height. Okay?
Because it doesn't the trapezoid that you're used to seeing doesn't mean that it is a trapezoid.
Mm-hmm. Questions about this problem? You guys are quiet today.
Wait, I have a question.
Uh-huh.
How did you get 36? Because
What's the base area of this rectangular prism is 6 by 3 is 18. The connector that connects the base to the top one is
I didn't see that the 3 was part of the base too.
3 by 6.
Okay.
And then
yeah,
the
and
2
then multiplied by 2. Okay.
Mhm. Anybody else? Okay. Try that one and see if you can get that 73.5. You don't need to put the answer in the chat because we can all see the answer. So now it's just, are you able to calculate that?
No, you can use like volume is used like for a lot of things. It's like is the volume of this. Like if we put this figure into this like let's just say for like the ramp, like let's just say it was for a skate park or something like that.
Mm-hmm.
Like the total volume or like the total area of this, like if it was of the total area of the skate park, and then would that ramp fit into where it's supposed to be if like the volume and area was matched to what it was supposed to.
I like drawing these, by the way.
Yeah.
I did a little bit better on this. Okay, 2 ways to do this. You could find the volume as if there was no piece missing from the top right corner and subtract that empty space from that. Or you can find the 2 separately and add them. You guys see what I'm saying? What if you pretend like that was solid and there was no piece missing out of the corner? and then you subtract whatever that piece is.
Oh, that would just be, that would be 1.5
By 1 by 7.
yeah.
And then you can just subtract that off of the whole thing.
Yep.
All right, so here we go. Base area of the little one is going to be 2.5. The height is going to be 7. So the volume is going to be 17.5 cubic centimeters. Now the big one, the base area I'm going to use is going to be 8. The height is going to be 7. And you're going to get a volume of 56 cubic centimeters. I'm going to add those together. I'm going to get 73.5 cubic centimeters. And then I look at the answer, not before. And I got it. So I will show you my screen so you can compare your work. Here I have the base area. I found that this here was 1 by 2.5. So 1 times 2.5 is 2.5. And then this length is 7. So you multiply and get that. And then this one is 4 by 2. So you get the 8. And then that's 7. So you get 56. Add the 2 together, 73.5. And then most students miss these on the test. For some reason, there's too many steps, and all you have to do is get one of the steps wrong and you get a lot more error made. Okay. I have a video for you guys that right now, let me assign you the homework. What lesson is this?
12.5.
12.5.
This one's going to be due tomorrow. (12.5) evens. You know, you start at the guided practice with number 2. You go all the way to the hot topic problem. And you go by evens. Questions? Okay. And now I would like to show you all a video about dimensionality that you might find neat. So let's turn this off. And I'll have to share my screen with you once I get it up. Be with you in just a moment here. Go. Just get rid of the ad first. Skip ad. Okay. Now I'm going to go ahead and share the screen with you. Okay. Can everybody see it? And then I'll need to share audio too. Wait a minute. Before I do that, I have to do, let me share screen. And then there's supposed to be a button that allows me to share the audio with you. You guys know how to do that?
I think, wait, did you press share screen?
Let me press share screen.
It's gonna share audio automatically, I think.
Okay, you guys let me know if you can hear it.
Discussing the large scales.
Can you hear that?
Cosmos, astronomers sometimes say that
Can you guys hear?
is curved,
Yes.
or that the universe is finite but unbounded. Whatever are they talking about? Let's imagine that we are perfectly flat. I mean, absolutely flat, and that we live appropriately enough, in a flatland, a land designed and named by Edwin Abbott, a Shakespearean scholar who lived in Victorian England. Everybody in flatland is, of course, exceptionally flat. We have squares, circles, triangles. We all scurry about, and we can go into our houses and do our flat business. Now, we have width and length, but no height at all. Now, these little cutouts have some little height, but let's ignore that. Let's imagine that these are absolutely flat. That being the case, we know, us flatlanders, about left, right, and we know about forward, back, but we have never heard of up, down. Let us imagine that into flatland, hovering above it, comes a strange three-dimensional creature which, oddly enough, looks like an apple. And the three-dimensional creature sees an attractive, congenial-looking square, watches it enter its house, and decides in a gesture of interdimensional amity to say hello. Hello, says the three-dimensional creature. How are you? I am a visitor from the third dimension. Well, the poor square looks around his closed house, sees no one there, and what's more, has witnessed a greeting coming from his insides, a voice from within. He surely is getting a little worried about his sanity. The three-dimensional creature is unhappy about being considered a psychological aberration, and so he descends to actually enter flatland. Now, a three-dimensional creature exists in flatland only partially. Only a plane, a cross-section through him can be seen. So when the three-dimensional creature first reaches flatland, it's only the points of contact which can be seen. And we'll represent that by stamping the apple in this ink pad and placing that image in flatland. And as the apple were to descend through, slither by flatland, we would progressively see higher and higher slices, which we can represent by the apple. So the square, as time goes on, sees a set of objects mysteriously appear from nowhere and inside a closed room and change their shape dramatically. His only conclusion could be that he's gone bonkers. Well, the apple might be a little annoyed at this conclusion, and so, not such a friendly gesture from dimension to dimension, makes a contact with the square from below and sends our flat creature fluttering and spinning above flatland. At first, the square has no idea what's happening. It's terribly confused. It's utterly outside his experience. After a while, he comes to realize that he is seeing inside closed rooms in flatland. He is looking inside his fellow flat creatures. He is seeing flatland from a perspective no one has ever seen it before to his knowledge. Getting into another dimension provides as an incidental benefit a kind of X-ray vision. Now our flat creature slowly descends to the surface, and his friends rush up to see him. From their point of view, he has mysteriously appeared from nowhere. He hasn't walked from somewhere else. He's come from some other place. They say, for heaven's sake, what's happened to you? And the poor square has to say, well, I was in some other mystic dimension called up. And they will pat him on his side and comfort him, or else they'll ask, well, show us, where is that third dimension? Point to it. And the poor square will be unable to comply. But maybe more interesting is the other direction in dimensionality. What about the fourth dimension? To approach that, let's consider a cube. We can imagine a cube in the following way. You take a line segment and move it at right angles to itself in equal length. That makes a square. Move that square in equal length at right angles to itself, and you have a cube. Now, this cube, we understand, casts a shadow. And that shadow we recognize. It's, ordinarily drawn in third grade classrooms as two squares with their vertices connected. Now, if we look at the shadow of a three-dimensional object in 2 dimensions, we see that, in this case, not all the lines appear equal. Not all the angles are right angles. The three-dimensional object has not been perfectly represented in its projection in 2 dimensions, but that's part of the cost of losing a dimension in the projection. Now, let's take this three-dimensional cube and project it, carry it through a 4th physical dimension. Not that way, not that way, not that way, but at right angles to those 3 directions. I can't show you what direction that is, but imagine that there is a 4th physical dimension. In that case, we would generate a 4-dimensional hypercube, which is also called a tesseract. I cannot show you a tesseract because I and you are trapped in 3 dimensions. But what I can show you is the shadow in 3 dimensions of a 4-dimensional hypercube or tesseract. This is it. And you can see it's 2 nested cubes, all the vertices connected by lines. And now the real tesseract in 4 dimensions would have all the lines of equal length and all the angles right angles. That's not what we see here, but that's the penalty of projection. So you see, while we cannot imagine the world of 4 dimensions, we can certainly think about it perfectly well. Now, imagine a universe just like Flatland, truly 2-dimensional, and entirely flat in every direction, but with one exception. Unbeknownst to the inhabitants, their 2-dimensional universe is curved into a 3rd physical dimension, maybe into a sphere, but at any rate, into something entirely outside their experience. Locally, their universe still looks flat enough, but if one of them, much smaller and flatter than me, takes a very long walk along what seems to be a straight line, he would uncover a great mystery. Suppose he marked his starting point here and set off to explore his universe. He never turns around and he never reaches an edge. He doesn't know that his apparently flat universe is actually curved into an enormous sphere. He doesn't sense that he's walking around a globe. Why should his space be curved? Because there's so much matter in this universe that it gravitationally warps space, closing it back on itself into a sphere. But our Flatlander doesn't know this. After a long while, you'll find he somehow returns to his starting point. There must be a 3rd dimension. Our Flatlander couldn't imagine a 3rd dimension, but he could sure deduce it. Now, increase all the dimensions in this story by 1, and you have something like the situation which many cosmologists think may actually apply to us. We are 3-dimensional creatures trapped in 3 dimensions. We imagine our universe to be flat in 3 dimensions, but maybe it's curved into a 4th. We can talk about a 4th physical dimension, but we can't experience it. No one can point to the 4th dimension. I mean, there's left, right, and there's forward, back, there's up, down, and there's some other directions simultaneously at right angles to those familiar 3 dimensions.
Well, what do you guys think?
I have a question.
That was cool.
So I have a question.
Uh-huh.
So can you please explain what the 4th dimension is? Because he didn't do that well of a job of actually explaining it.
You just said the 4th dimension. That's it.
That wasn't what the video was about.
Time is the 4th dimension.
Yeah, it would be time. So if you're trying to think that time would be at a right, it's going to be hard to think about it because you're not.
We live in time. We can't
You can perceive that time is passing, but you
we
can't
can't
see it.
change.
You can't hear it. You can't see it, and you can't really even imagine it. All you can do is experience that it's happening, like a shadow. Like us experiencing time is almost the shadow of the dimension. and it's at a right angle to our 3 dimensions, to all of it.
Wow.
So if you think about, I mean, in that last step where we made 2D into 3D, you had a 2D, and how did we stretch it into a 3rd dimension? Every point along it, the whole thing, not just one point, but all of those points stretched in the same direction along the same vector path. Okay? Until you had, right? All of them stretched the same amount in the same direction until you had, and you stopped, that was your stopping point, right? And that bounded your 2D, what you had is a 2D. And then we took this thing and we stretched every point, even the ones inside, every point, all of them stretched it toward us. Well, stretching what we have in 3 dimensions, how would you stretch it and in what direction? Well, I guess it would be in the direction of time, right? You're stretching it through time, I guess. I don't know. Hard to imagine what that looks like, but you're experiencing it right now.
So the 4th dimension would be time.
Yes. And you're experiencing time passing is the stretching of the 3D through time.
What is the 5th dimension?
I don't know.
Rosenthal, I have a question.
Mm-hmm.
So you've seen Back to the Future, right?
What?
You've seen Back to the Future, right?
Yes.
So you know the DeLorean?
Yes.
Who made the DeLorean?
Who came up? Who designed that car? I don't know.
No, I mean like in the movie.
John
Oh,
DeLorean.
it was. It would have been Doc Brown.
No, but he got the design from his future self.
Yeah.
So
Not in the original. Oh, you mean in the original?
yes, he goes back in. The kid goes back in time to escape the terrorists.
Not in the first place. Though in the original, he bumped his head and came up with the idea for the flux capacitor, which is what makes time travel possible in the movie.
I know, but he goes back in time, and the guy's like, "Oh,
That's after, though.
oh."
You couldn't go back in time unless you already had the invention in the first place.
Yeah.
I know, but he got the invention from his past.
That might eventually have been, but originally he did not get the invention that way.
But isn't it infinite loop? Didn't the kid come back and see his past self doing the exact same thing?
Well, you're asking me about the physics of a movie where time travel is not possible as we know today.
Technically, it is.
Well, we are traveling through time forward, but not backward.
Quantum theory.
To go backwards in time, there's nothing. The evidence mathematically shows you cannot do that.
What would it be if you traveled side to side, like through time?
Maybe those are alternate realities. I don't know.
Ooh, that would be cool.
And up and down also, right?
Quantum physics explains time, right?
I don't know.
With time, you can't really go side to side without traveling through dimensions. Like, for example, a 2D line, right? A 2D line, imagine that as time.
A 1D.
And it has multiple, or 1D, sorry. It has multiple other lines next to it, right? Those are the different dimensions. So if time travel is possible, you can go forward and backward through those,
Time
but
is
it would be extremely difficult to go through the other dimensions.
Yeah, like also, or you could imagine it like it's like a horse race, and each person, it's like a running marathon, and each person has like a lane they have to stay in, and if you like cross diagonally, that's another dimension you're in. So you can think of it like that too.
There are actually time travel theories.
Yeah, you guys can have fun looking those up because I don't know much about them.
Space.com.
All right, so we're in office hours now. If you didn't notice, you guys are free to go. If you didn't know.
Thank you.
Thank you, Mr. Rosenthal.
All right.
Oh, thank you so much.
Betcha.
Bye.
Bye.
Mr. Rosenthal, I'm sort of confused on example number 2. Like, how do you find the base of a triangle?
Okay, so in example 2, I have to bring that back up because I don't know what example 2 looked like.
Mr. Rosenthal, I gotta get to another lecture.
Okay.
We can do algebra tomorrow though.
You got it.
Bye. Thank you.
Bye. You got it. Okay, this was example 2.
Yeah.
Okay, so this was 6. So the one above it is 6. This is 7. So this is 7, and the one in the back is 7. This is 2. So you have this triangle is a base.
Uh-huh.
You find that with this. So 1/2 times 6 times 2 is 6.
So the 6 is because of the
This is,
because it's half of a square because it's half of a square. So you do.
and there's the formula though, half the base times the height.
So what if it's like in a regular triangle that doesn't equal a square?
Then it's still, so if you have this like an obtuse triangle like that,
Yeah.
okay, and let's say that this was 6, the height would have to be the straight up and down. They would have to give that to you. It would not be the slant.
Okay, so
It would be 2, and it would still be an area of 6 square centimeters.
so it tell you, and then you could subtract it out.
Yeah, because the area of a parallelogram that's not a square is still base times height.
Uh-huh.
But it has to have dimensions have to be perpendicular to one another. So
But you can't subtract. But how do you know the
slanted
color
one,
diamond?
the slanted one cannot be the height. It must be straight up and down. What was your question?
So how do you find the gray area so you can subtract that out?
What
Or
gray area?
So you have the triangle, and then you have your dotted lines showing the square rectangle that's in. So you've calculated the rectangle. How do you know how much to subtract?
I'm not calculating any rectangle. I know that if I stretch my triangle now down 7 centimeters, all I have to do is take my area of 6 and multiply it times how far I stretch it down, times 7. And then I get 42. And that's
Okay.
and it's cubic now because this was centimeters squared and this is centimeters. So centimeters squared times centimeters to the 1 is centimeters cubed.
Okay.
Does that make sense? I'm stretching the triangle 7 centimeters.
Okay.
The entire thing. Every point inside the triangle is being stretched the same 7 centimeters.
Okay. Thank you.
You betcha.
Bye.
Bye. Anybody else?
Yeah, I have a question.
Mm-hmm.
For number 8 on the chapter 9 test, I didn't really get how those were triangles. I was kind of confused.
Okay, you got to give me the problem. I don't have that in front of me.
Oh, okay. 2 similar triangles are shown on the coordinate plane.
Uh-huh.
How can you use these figures to draw a conclusion about the slope of the parallel lines?
You had something like that, right?
No, we got two lines going over. We didn't get triangles.
Yeah, but you can connect them, right?
Oh, wait. Okay, that's what I was having trouble on.
Right? Okay, so if 2 triangles are similar, then the ratios of corresponding sides are equal. So if this is A and this is B, and then this is C and this is D, okay, then A corresponds to C as B corresponds to D. See that?
Yeah.
Okay, now with properties of proportions, we also know that A is to B as this C is to its D. That is also true. Okay, because of you can just cross multiply and divide and manipulate and get it to look like that. We called it the side to side property, right? A is to B as C is to D. I don't know if you remember that.
Yeah, I think I remember a little bit of that. It's been a while though.
But look at A, the ratio of A to B. That's rise to run. That's slope. That's delta Y over delta X. And look at C to D. That's a rise, and this is a run, right? So those are slopes. So we're saying that because the triangles are similar, then the ratios, which are the slopes, are equal. Okay, and that, so the conclusion we can make is that if two lines are parallel, then their slopes are equal. And the question was, how do we use what we know about similar triangles to do that? So we would want to say that when two triangles are similar, the ratio of, the ratio of corresponding sides is proportional. And so the slopes would be equal.
B equals D and A equals C.
It doesn't equal it. Like C is bigger than A, but there's some scale factor. Say, let's call it K. If I multiply A times K, I'll get C, which means that I have to multiply B by the same exact number that I did A, and that would give me D. I don't know if you can see it that way.
Yeah, I can kind of see it that way.
When I have a fraction like 3/4, if I multiply the top by the same amount as I do the bottom, then I get something that's equal to my original.
Oh, okay. That makes sense.
It's not that 3 is equal to 6. It's that the 3 to 4 is equal to 6 to 8. So the 3 can become a 6 if you multiply it by some scale factor that you would also multiply to the bottom. And that would keep your ratio equal. Why does it keep it equal? Because when you multiply by the same as on the top and on the bottom, you're really multiplying by 1, identity property.
All right. Thank you. I was having trouble with it. I didn't understand like how they were triangles too. And
Thank you, Mr.
yeah,
Rosenberg.
I knew I didn't understand it on test.
Okay.
So I used what I knew and then I tried to explain that way, but yeah. And when I was going over the test, I didn't understand it. So.
Thank you for coming back to clarify it. I love when students care about the learning process and not necessarily about the grade.
All right. Thanks.
All right, you betcha.
Bye.
Bye. Anna, Flynn, Andy, anybody have any questions for me at this point? All right, I'm going to end session. Have a great day. I'll see you tomorrow.